Good afternoon. Thank you for watching our presentation video. This video presents our work. Hugs are better than handshakes. Unsupervised cross-modal transformer hashing with multi-granularity alignment at BMVC 2022. Hashing has been a popular indexing strategy for large-scale multimedia data because the Hamming descriptors can accelerate cross-modal retrieval with fast exclusive OR operators. Unsupervised cross-modal hashing is a practical task that learns to generate binary representations for different modalities, such as images and texts, without requiring manual label information. In the UCMH settings, we are given labeled text-image pairs as training samples. The quality of hash representations is inherently subject to multimedia understanding. Although neural networks have made remarkable progress in hashing, the advances of deep learning have yet to be fully exploited. State-of-the-art approaches mainly used classic convolutional neural networks, such as VGGNet and AlexNet, to extract visual features, and used multilayer perceptrons to encode text information. These designs are suboptimal to capture semantics from visual and linguistic data, and they also suffer from limited transferability. To improve UCMH and keep pace with the development of deep learning, one promising direction is to explore transformer-based methodology. In the past few years, transformers have shown excellent talents in computer vision and natural language processing tasks, sparking explorations toward better machine understanding. Pre-trained on large-scale corpora, transformers can serve as versatile experts that are effective and generalizable for various downstream tasks. A typical manner for cross-modal retrieval is to train the transformer-based models by aligning CLS tokens. As transformer-based cross-modal hashing remains underexplored, we are interested in how UCMH can benefit from transformers. Although pre-trained transformers provide solid semantic extraction for each modality, the task of UCMH is still non-trivial. The main challenge is to bridge heterogeneous modalities so that the hash codes can be well aligned. Analogous to existing CNN-MLP-based models, we can train transformer-based UCMH models to produce hash codes via the CLS tokens. A simple way for learning is to align the global tokens using the objectives in existing UCMH methods. As shown in Figure A, we call this global alignment strategy by handshaking. In practice, handshaking is effective as expected but can be improved to reduce the modality gap. Note that transformer is a sequential architecture that arranges inputs as sequences. It naturally provides a set of content tokens, for example, words of a text or patches of an image. These tokens convey fine-grained and structural semantics and can capture heterogeneous modality knowledge. As illustrated in Figure B, we present a multi-granularity alignment framework dubbed Hugging. Hugging enhances transformer-based UCMH training with fine-grained alignment based on content tokens. Fine-grained alignment is an auxiliary task and is removed after finishing training. Thus, it will not increase extra inference overhead. We instantiate the Hugging framework by building a simple Hugging hash model with contrastive learning for global alignment. For fine-grained alignment, we construct another shared latent space with semantic structure via a Ghost VLAD module. Each content token in this space is softly assigned to a series of parameterized clusters, each representing a latent topic or semantic concept. Cluster-wise contrastive learning serves as an auxiliary objective for model training, which enhances cross-modal consistency of the learned hash codes. We use a pre-trained BERT as the text encoder and a pre-trained vision transformer as the image encoder. We forward the output embeddings of CLS tokens, denoted as X, to the hash module. The hash module comprises a linear layer and a scaled hyperbolic tangent function. Alpha in equations 3 and 4 denotes the scaling factor. SG is the stop gradient operator that is the identity function in the forward pass but drops the gradient for variables inside it during the backward pass. By equations 5 and 6, we can directly pass the gradient straight through the binary hash codes, such that the hashing learning can be end-to-end. The global alignment loss function is written by equation 7. It directly aligns the text and image hash codes. We present a clustering-based strategy with Ghost VLAD for fine-grained alignment. Our basic idea is to exploit concept-aware semantics and enable concept-aware alignment in the latent space. Specifically, we first project the output embeddings of the content tokens into a shared latent space according to equations 8 and 9. Then, we learn to align semantic information with a series of cluster centroids. We designate C0 as the ghost centroid to filter noise, such as uninformative words in a sentence and background features for an image. We forward projected content embeddings to Ghost VLAD. Each embedding will be softly assigned to all clusters according to equation 10. After clustering, we aggregate modality-wise residual embeddings at each cluster except the ghost cluster. Equation 11 formulates the residual computation process respective to the ends cluster. Finally, we define the fine-grained alignment loss by equation 12, which summarizes cluster-wise contrastive learning loss terms. Here we summarize the learning objectives of Hugging Hash by equation 13. R quant is the quantization loss. Lambda and gamma denote the hyperparameters for balancing different loss terms. The Hugging framework is highly flexible and compatible. By replacing GA loss with other hashing objectives, we can easily extend Hugging to existing methods. During retrieval, we rank the retrieved items given a query according to the Hamming distance between hash codes. Take text-to-image retrieval as an example. The Hamming distance is defined by equation 15. In the experiment section, we first compare the proposed Hugging Hash with UCMH SOTAs in terms of retrieval performance and transferability. Table 1 benchmarks different UCMH baselines on 3 widely used datasets. To explore the impact of transformers on UCMH, we adapt open-sourced implementations of 4 representative baselines, namely DBRC, DJSRH, DSAH, and DGCPN, by using the same backbones as Hugging Hash. The same methods in the transformers block outperform those in the CNN plus MLP block by considerable margins. It verifies that pre-trained transformers provide better modality understandings than CNNs and MLPs, thus contributing to high-quality hash codes. Besides, on all settings, Hugging Hash outperforms transformer-based baselines that only consider global alignment. In terms of global alignment for hash codes, although Hugging Hash adopts a simple contrastive learning objective that is much simpler than the baselines, the superior results it shows indicate the effectiveness of exploring multi-granularity alignment with transformers beyond global alignment itself. On the model transferability, we conduct a multi-dataset, Flickr and MS-COCO, evaluation with DBRC, DJSRH, DSAH, DGCPN, and the proposed Hugging Hash. We compare standard, id-est, train and test on the same dataset, and zero-shot performance, id-est, train and test on different datasets. We also investigate different backbones. To deal with different vocabularies between datasets, we replace the bag of words features with the word2vec features as the text inputs for vanilla CNN MLP variants. BERT plus VIT indicates transformer-based variants using global alignment. BERT plus VT Hugging indicates the variants with Hugging. We can learn from Figure 1 that transformers not only boost in domain performance but also improve generalizability. Using the proposed Hugging framework can further improve the zero-shot performance in most cases. We notice that Hugging Hash shows the best zero-shot performance on both datasets. The reason is that the contrastive learning objectives help to produce more transferable hash codes. To better understand the mechanism of fine-grained alignment, we investigate how different cluster in Ghost VLAD looks like. As a case study, we pick up the text-image pairs associated with 3 single labels: cat, dog and truck. Each text or image is represented by multiple content tokens. Figure A visualizes the token distribution by different labels and modalities. The black stars mark the centroids. For quantitative analysis, we also compute the class-specific and modality-specific average assignment scores with respective to all clusters, as shown in Figure B. The general consistency between the text and the image assignments to each class implies the effectiveness of cross-modal structural alignment. Besides, the assignment patterns can be different among labels. The truck exhibits a uniform pattern, while the cat and dog present a concentration on the first, fifth and seventh centroids. In particular, we hypothesize a connection between the seventh centroid and the concept of animals. We also investigate the effect of transformers and the Hugging framework on SOTA UCMH methods. We report some results in Table 2. Firstly, we can see consistent improvements. Besides, we can learn that SOTA UCMH methods surpass Hugging Hash when equipped with Hugging. This is reasonable because they use more complex global alignment mechanisms. Here we list the conclusions. First, we propose Hugging, a multi-granularity learning framework for transformer-based UCMH. Second, we instantiate Hugging by building a simple Hugging hash model with a contrastive learning objective and demonstrate its merits on 3 datasets. Third, we also adapt several state-of-the-art UCMH methods using Hugging, verifying its feasibility on transformer-based UCMH. Thank you for your watching.